one of the skills we need is to be able to sketch an endothermic and an exothermic reaction as a graph, and we need to be able to label the key parts of that graph. The other thing that we're challenged to do is to understand what would happen if we change the starting conditions a little bit. In particular, things that are related to the collision theory. So we're just going to start by doing a quick revision on what the collision theory states. For a successful collision, so a reaction, to occur, what things are required to happen? Okay, so you said activate, so enough energy. Yep. So the collision has to have enough energy. And you've very correctly said that's called activation energy, which I'll use the symbol E, little a for. Well done. So there has to be a collision, doesn't there? Yep. The name sort of implies it, so that was good. So there has to be a collision. But when it's not just a collision. Think about Lego blocks. If I put two Lego blocks together, and I just put them end to end, are they going to stay together? No. So what do I have to do? I have to collide them in the correct... Sorry? Yep. Correct way, correct orientation. So orientation is important. Okay? The orientation of the molecules or ions, particles, let's say, has to be correct to allow a successful collision. Anything else that's required? Oh, sorry, I didn't write one up about the collisions. So you need some collisions. So from our work last year, what do we know about how to make a collision more likely to be successful?
Increasing the temperature.
Great, I can increase the temperature. What does that do to these? Makes the particles go faster, which means there's going to be more
Kinetic energy.
Great, more kinetic energy, so there'll be more collisions because they're going faster, and more of the particles will have enough energy to collide successfully, so react. Cool. So it actually does two of them really well, which means by probability, more collisions means more of them will be with the correct orientation. What else could I do?
Concentration.
Increase concentration. Awesome. That only really does one of them. But which one is it that it increases the frequency of? Or collisions. More collisions, good. And there's one more.
Catalyst.
Catalyst. There's actually two more, but for this, we're only going to worry about this. Whoops. Introduced a catalyst. Now, catalyst is a chemical, whether it's a protein, so an enzyme, or whether it is a heavy metal like iron or vanadium, something like that, which provides an alternate pathway. What it basically does is it makes sure that when they collide, more of the particles are in the correct orientation. Okay, so it has an effect there. What that does, though, is it means that because there's an alternate, easier pathway, less activation energy is required for a successful collision to occur. Okay, so that's the effect that that one has. We need to be able to show these two on a graph. I can't show concentration on these graphs other than to squeeze it up that way. It happens faster, but it has no effect on the actual shape, so we don't tend to look at the concentration. But we do need to know what would happen if we increase the temperature. Okay, so the first thing I want to know is what type of reaction or change is shown by the first graph. What's the first graph showing me? What type?
Exothermic.
Great, so this is exothermic. So we've got that nice skill of being able to recognise. Conversely, therefore, the other must be endothermic. Cool. Now let's say, for argument's sake, they both show different reactions that are occurring in the absence of a catalyst and at room temperature. So about 20-25 degrees Celsius. What would happen, I'm just going to number these now because we're going to use different graphs on these are key. I'm going to use a black line to show what happens when a catalyst is present, and I'm going to use a red line to show what happens when I increase the temperature. So, if enthalpy, and sorry I forgot to label my axis here, if enthalpy is my y-axis, and enthalpy is the total energy approximately. If I increase the temperature, what will that do anything to the initial enthalpy? If it starts at a higher temperature, is that going to affect the energy of the particles? Yes, because they'll be moving faster. So kinetic energy is part of this thing called enthalpy. So that means I'm going to start at a higher value. So let's say it's here. Okay, I'm not going to carry my graph off. I'm going to go through some things. Do you think it changes the amount of energy required for successful collisions to occur? In other words, the activation energy. Will it change that value? No. So you're saying that I'll add red going through there?
Yeah.
Same point. Do you think it will change the final enthalpy of the products?
Yes.
How?
It'll be warmer.
Fantastic. Because it's warmer, this will be higher, won't it? Because even at the end, the particles have more kinetic energy than in our control, as it were. This is important. You get a ruler, or fingers, and you match that same distance there. Okay? The enthalpy change, so from here to here, has to be the same as from here to here. No matter what the temperature, unless you're causing phase changes, so different states of matter, no matter what the temperature you start at and end at, the enthalpy change stays the same for each chemical reaction, roughly. So we match the graph shape so it looks like that. And so you can see with a higher temperature, it doesn't look much different. But what's really important is that its activation energy stays the same. That's the amount of kilojoules per mole that is required for a successful collision to occur. Cool. So we'd need to be able to do the same thing here. We'd need to be able to match that. So let's start at this temperature here. I'm sorry, I'm not going to go quite so high because it creates a problem. Okay. Will the activation energy be the same, lower, or more?
Same.
Same. So we're going to hit this point here. And will my final enthalpy be the same, higher, or lower?
Higher.
Higher. Be specific. Higher.
Because it'll be warmer at the start.
So by how much?
2 fingers away.
That there?
Yeah.
Goes to there. Fantastic. So these are sketches you need to be able to do. Whoops. You can see why I was being careful not to go too much higher. Okay. So higher temperature. The graph looks slightly different, not hugely. Key point is EA stays the same. Okay. What about, change to a black pen now, what if I have a catalyst instead? So I'm going to keep the temperature at the original temperature. Will a catalyst change the enthalpy of the particles that are present prior to reacting?
No.
No, because they're not an energy themselves, they're a substance. Therefore, will they change the enthalpy of the things at the end?
No.
Okay, what do they do then?
Or the activation energy.
Good. By providing an alternate pathway, they lower the activation energy. Because it's a sketch, we can make it up. But honestly, we just make it up. Oh, let's go there for my EA catalyst. Whoops, be nice if I could actually spell catalyst. So I'm going to go like this. So I've got a new shaped graph. It's not hugely different, it's just slower. And so I'd be able to tell you why, or you'd be able to tell me why this reaction occurs faster, even though the enthalpy change is the same and there's no change in temperature, or to the speed of the particles, therefore. Likewise here, let's make up a new EA. Because they're just sketches, so we can make things up. Sorry, I put it slightly above just so that the 2 black and blue lines can be seen separately. Those are the sorts of things you're expected to do with the sketches. The other thing you're expected to do, we've labelled the EA, but there's one other thing you are expected to show, and that is the enthalpy change. I'm going, oops, sorry, wrong colour. I'm going to use my blue pen, so you're looking at the control one. So here's my blue initial line, here's my blue final line. So if I bring this one back here, I can find my enthalpy change. Notice it's an arrow going down for exothermic because it will be a negative value. It's going from here to here. In an endothermic, extend this out. Notice the arrow is going up because you're going from here to here. So it's going to be a positive value. Right, are there any questions before I stop the video?